In this session, we are going to see force voltage analogy. That is, we are going to map mechanical translation system into electrical circuits. So, before that, we need to know the basics related to electrical systems. The model of electrical system can be obtained by using resistor, capacitor, and inductors, that is RLC. The differential equations governing the electrical system can be formed by Kirchhoff's current law by choosing various nodes in the network, or Kirchhoff's voltage law equations by choosing various closed path in the network. This is the basic related to electrical systems. Now we are going to discuss about the basic elements and their differential equations. First, we are going to consider resistor. So, R is the resistance value, V of t is the voltage across the resistor, and I of t is the current through the resistor. Using Kirchhoff's voltage law, V of t is equal to R into I of t, and the current through the element I of t is equal to V of t by R. Next, we are going to consider inductance. So, this is the inductor. Voltage across the inductor is V of t, and current through the inductor is I of t, and the inductance is L, represented using L. So, the V of t, voltage across the inductor V of t is equal to L into di of t by dt. At the same time, the current through the inductor is equal to 1 by L into integration V of t into dt. Next, we are going to discuss about capacitor. So, it's a storing element. The voltage across the capacitor is V of t, and current through the capacitor is I of t, and the relationship between V of t and I of t because of the capacitor is V of t is equal to 1 by C integration I of t into dt, and current through the capacitor is I of t is equal to C into dV of t by dt. Now we are going to map these element with mechanical systems. Okay, so we have resistor, capacitor, and inductor, and their equivalent mechanical system we are going to discuss. First, we are going to consider a dashpot. So here a dashpot is connected with the reference, and when you are applying force in one side, dashpot is moved, and the velocity is recorded registered as V is equal to dx by dt, and the x is the displacement because of the force, and the force balance equation is F is equal to B into dx by dt, and which can be written like B is equal to B into V, because V is equal to dx by dt. And this dashpot is equivalent to resistor. Okay, resistor, that is current voltage across the resistor, that is E is the applied voltage, that is E is equal to V. V is the applied V is the voltage across the resistor, and voltage across the resistor is equal to R, resistance value R into current flow through the resistor I. So we can simply write E is equal to R into I. So V is equal to Ri, and E is the applied voltage, and V is the voltage across the resistor. So applied is equal to the voltage across the resistor, which is equal to R into I. So here input is voltage, and output is current through the element. Next one is mass element. A mass element is connected with the reference, and a force is applied, and the mass element value is m, and because of the force, the mass element will move from one place to another place, and that is recorded as a displacement, and and the mass element M is equal to M which is connected with the force balance equation is F is equal to M into dx by dt square, and which is equal to M into dv by dt, because the acceleration A is equal to d square x by dt square, which is equal to dv by dt, rate of change of velocity and rate of second order derivation of the displacement is equal to acceleration. Now this mass element is equivalent to an inductor. Okay, an inductor is connected with the voltage source, and is the voltage source, supplied voltage source, and V is the voltage across the inductor, and now force the force balance equations, that is E, here voltage equation using Kirchhoff's voltage law, E is equal to V, this applied voltage is equal to the voltage across the inductor, which is equal to L into rate of change of current di by dt. So simply we can write the applied voltage E is equal to L into di by dt. Next one is spring. Spring is connected with the reference, and spring constant is K. A force is applied. Okay, a force is applied. Because of the force applied, the spring will sometimes get because of applied force depends upon the direction of the force, the spring will get expanded and compressed. Here force is in this direction from left to right, so the spring will get compressed. The velocity is recorded as v, and the displacement is x, and this x is equal to integration v into dt. Okay, velocity v is equal to rate of change of displacement, and when you are integrating both sides, we get integration of v into dt is equal to x. So the force balance equation is the applied force is equal to k into x, that is displacement, which is equal to k into, we are substituting the value of x, integration v into dt, and this spring, since it is compressing and expansion, is equivalent to a capacitor. A capacitor is connected with the voltage source, is the voltage source, and C is the capacitor value, and V is the voltage across the capacitor. So applied voltage is equal to voltage across the capacitor, which is equal to 1 by C into integration I into dt. E is equal to 1 by C into integration I into dt. These are the basic elements. Now I am just relating the terms and the notations related to mechanical system and electrical system. Here in mechanical system, force F is equivalent to voltage E or V, velocity V is equivalent to current I, displacement x is equal to charge q, frictional coefficient B is equivalent to R, mass M is equivalent to inductance L, spring K is equivalent to inverse of capacitance 1 by C, Newton's second law, that is sum of forces and the node is equal to 0. Here we are using Kirchhoff's voltage law, sum of voltage is equal to 0. So that is actually force voltage analogy. Now we are going to discuss force current analogy. In mechanical system, input is force and output is velocity. In electrical system, input is current and output is voltage across the element. Now we are going to take a dashpot first. A dashpot is connected with the reference. A dashpot is connected with the reference. Here applied force F, force is applied on the dashboard, and force balance equation is F is equal to B into dx by dt, and this is equivalent to a resistor R. Okay, a current source is connected with the resistance. Now voltage across the resistor is V. Now when we are relating is I is equal to 1 by R into V. At the same time, mass element. Mass element is equal to capacitor. Here in Ford's voltage analogy, mass element is equivalent to inductance. In Ford's current, mass element is equal to capacitor. So here it is a mass element, and F is equal to m into d square x by dt square, and here the current input I is equal to voltage across the capacitor C into dV by dt. At the same time, spring is equivalent to inductance. Okay, here spring is connected with the reference, and the force balance equation is F is equal to K into X. K is equal to K into integration V into dt, and is equivalent to inductance is connected with the current source. So the I is equal to 1 by L into integration V into dt. So these are the introduction related to force current and force voltage analogy. In Ford's current analogy, input is current and output is voltage across the element. Now I am going to relate the terms and the parameters or notations related to mechanical and electrical system. In mechanical system, force is represented as F, and it's equivalent to I. Velocity V is equivalent to voltage. Displacement X is equivalent to flux. Frictional coefficient of dashpot is equivalent to conductance, that is G is equal to 1 by R. Mass element M is equivalent to capacitance, and spring K is equal to inverse of inductance, and Newton's second law, sum of forces acting on a load is equal to 0, and here sum of current in the node is equal to 0. Based on these parameters and introduction, we are going to solve a problem. So I will read the problem. Write differential equation governing the mechanical system shown in figure. Draw the force, voltage and force current electrical analogous circuits and verify by writing mesh and node equations. Here you are seeing two mass element 1 and mass element 2. Okay, mass element 2 is connected with the reference. In between we have a spring and a dashboard, and in between mass element 1 and 2 again we have a spring and a dashboard, and force is applied on mass element 1 m1, and displacement with respect to mass element 1 is x1, and velocity with respect to mass element 1 is v1, and displacement with respect to m2 is x2, and velocity is v2. So the friction between the mass element and the reference is represented by b1. Okay, by seeing this mechanical translation system, we can assume that there are two nodes are present because there are two mass element present. So we have to write free body diagram for mass element 1 and then free body diagram of mass element 2. Using these two equations, we are going to find the transfer function. From that we can change into force voltage and force current analogous circuits. Now first we will consider mass element 1. So when you are considering mass element 1, there are 1, 2, 3, 4, 5 forces are acting. One force is applied and other forces are opposing force. Opposing forces are due to mass element 1, due to spring K1, dashpot B12 and the friction B1. So applied force F1, Fm1, B1, Fk and Fb12. Now the equation related to these opposing forces are given here. So Fm1 mass element is Fm1 is equal to m into dx1 d square x1 by dt square. Fb1 is equal to b1 and dx1 by dt, and Fb12 is common, is in between m1 and m2. Hence we have to consider two different displacement with respect to mass element 1 and displacement with respect to mass element 2. So Fb12 is equal to b12 d into x1 minus x2 divided by dt. Similarly, we have to consider K1. K1 is in between M1 and M2. Here also we have to consider two different displacements. So Fk1 is equal to K1 into x1 minus x2. Using Newton's second law, forces, sum of forces acting on the node is equal to 0. Here we have one applied force and the other forces are opposing force. So these are all opposing force, which is the sum of opposing force is equal to applied force F of t. Now we have to substitute the equations related to Fm1, Fb1, Fb12, Fk1, and when you are substituting it, you get this equation, and we have to assume this is equation 1. Similarly, we have to write equation related to mass element M2. In mass element M2, there are again 5 forces are acting. One force is related to mass element M2, and other forces are because of the friction and the spring, okay, that is dashpot and spring. So Fb2 is related, is actually dashpot is connected to the reference, and K2 is, that is spring, is connected to the reference, and K1 and B12 is common to M2 and M1, that is node 1 and node 2. So we have listed the opposing force on M2, that is Fm2, Fb2, Fb12, Fk1 and Fk2. Now the equations related to all these opposing forces are given here. So Fm2 is equal to m2 into d square x2 by dt. So x2 is the displacement related to mass element m2, and Fb2 is equal to b2 into dx2 by dt. B12 is equal to B12 into dx2 minus x1, because this B12 is common to M2 and M1. Now we are going to consider mass element M2. So first we have to consider the second displacement, that is x2 displacement, and then we have to subtract from the first displacement. So x2 minus x1. Fk1 is common to M2 and M1, hence yes, Fk1 is equal to K1 into x1 minus x2, okay, and K2 is equal to, sorry, Fk1 is equal to x2 minus x1, and Fk2 is equal to K2 into x2. By Newton's second law, forces acting on the node is equal to 0. All are opposing force. So Fm2, Fb2, Fb1, B12, Fk1 is equal to 0. Now we have to substitute the equation related to all these opposing forces. Fm2 is m2 into d square x2 by dt square. Fb2 is b2 into dx2 by dt. Fb12 is b12 dx2 minus x1, and then Fk1 is K1 dx2 minus x1, which is equal to 0. 1, 2, 3, 4 plus Fk2. So Fk2 is here. Fk2 plus Fm2 plus Fb2 plus Fb12 plus Fk1 is equal to 0. Now we have two equations. Now we are going to replace the displacement by velocity in the differential equation. So first part in finding force voltage analogy, we have to replace displacement with velocity. For example, if you are taking d square x by dt square, then we can put in terms of we can replace by dv by dt. If you find dx by dt, then you can replace with v, and if you have x, then you can replace with integration v into dt. So we are going to write equation 1 and 2 in terms of velocity v. So here this is equation 1, m1 and d square x1 by dt square. We are going to change displacement with velocity. So d square x1 by dt square is equal to dv1 by dt and b1 plus b1, dx1 by dt is equal to v1, b12 here, and dx1 minus x2 by dt is equal to v1 minus v2. Okay, k into x1 minus x2 is equal to k1, and x1, if you have x, then you have to replace with integration v into dt. So integration v1 minus v2 into dt is equal to f of t. So we simply changed the displacement with velocity. So this is the terms. Wherever you find d square x by dt square, you have to replace with dv by dt. If you find dx by dt, then you have to put v, and if you find x, then you have to put integration v into dt. So simply we have changed equation 1 in terms of v. Similarly, we are going to change the second equation. Second equation is m2 into d square x2 by dt square. So m2, so here d square x2 by dt square, I am going to replace with d v2 by dt, here b2 plus b2, dx2 by dt is changed by v2 plus k2, x2 should be replaced with x into dv by x equal to integration v into dt. So x2 is integration v2 into dt, b12 dx2 minus x1 by dt. So v1 minus v2 minus v1, and k1 x2 minus x1. So integration v2 minus v1 into dt, which is equal to 0. Now electrical analogous element of mechanical system, we are going to map electrical and mechanical elements. So force is equivalent to that is applied voltage, and V1 is equal to I1, V2 is equal to I2, mass element is equal to L1, and mass element 2 is equal to L2, and spring K1 is equivalent to 1 by C1 and K2 is equal to 1 by C2. Dashpot friction B1 is equivalent to R1, B2 is equivalent to R2, B12 is equivalent to R12. We are going to simply replace the terms. Okay, where we are not doing anything. We are going to simply replace the terms. That is, when you find V, you are going to replace with I, and V, that is V1 I1, V2 I2. At the same time, if you find force f of t, then you are going to put E of t. I'll start with force. F of t is replaced with E of t. Then M1, just see this here and you can directly write it. M1 is equal to L1. dV1 by dt is equal to V, we have to replace with I1. So dI1 by dt plus B1 is equivalent to R1, V1 is equivalent to I1 plus B12 is equivalent to R12. This is V1 I1, V2 is equivalent to I2. K1, just see this, K1 is equal to 1 by C1, okay, 1 by C1 integration V1 is I1, V2 is I2 in dt. So this is the differential equation related to electrical circuit. Just see this. A voltage source is here, okay, is a loop equation. A voltage source is here, and inductance is here, a resistor is here. There are two resistors, and the second resistor is common to first loop and second loop, that is I1 and I2. I1 is the current in the first loop, I2 is the current in the second loop. So we can assume that there are two loops. Okay, I am starting with E of t. E of t is here, a current source, then an inductor. So I have used an inductor, then one resistor I1. So this is the resistor, and R12 and C1 capacitor is common to loop 1 and loop 2. So R1 I have given, R1 is common to loop 1 and loop 2. This loop current is I1 and this is I2, R12, and then the capacitor is C1. So the resistor and the capacitor is series and common to loop 1 and loop 2, and L1 and L2 is series with the voltage source. So this is the equivalent circuit. Okay, so we started with mechanical system, and we have obtained electrical equivalent circuit for the first equation. Similarly, we are going to change the second equation and draw the circuit. So we have second equation, and simply we can change this M2 to L2 dV2 by V2 by dt di2 by dt plus B2 is equivalent to R2, V2 is equal to I2 plus K2 1 by C2, V2 is equivalent to I2 is dt, then B12 is equivalent to R12, V2 I2, V1 I1 plus K1 1 by C1, V2 is I2, V1 is I1, is dt is equal to 0. Here two elements are common. One is R12 and 1 by C1. So R12 and C1, these two are common to loop 1 and loop 2, and in addition to that we have a capacitor, resistor and inductor. Inductor, then capacitor and resistor, that is L2, R2 and C2. Simply you have written the second loop, and the output is taken here across the resistor and capacitor. So this is the equivalent circuit of the second equation. Now we are going to combine first and second circuit. Okay, this is the first circuit and second circuit. So we are simply joining, because these two terms, these two elements are common to both circuits. So I am simply joining and drawing the final circuit. This is the force voltage analogous circuit for a given mechanical translation system. Similarly, I am going to draw electrical equivalent circuit for the given mechanical system. So force current analogy circuit for a given mechanical system. In force current analogy, F of t, the force is equivalent to current, velocity V1 is equivalent to voltage V1, V2 is equivalent to V2, that is velocity is equivalent to voltage, mass element is equivalent to capacitor, and friction dashpot is equivalent to conductance 1 by R12, and spring is equivalent to reciprocal of inductance. I am simply replacing the terms in the first equation and the second equation, starting with force equivalent to current, then mass is equivalent to capacitor, V, that is velocity, is equivalent to voltage, B is equivalent to conductance, that is 1 by reciprocal of resistance, V, there is no change, that is voltage is equivalent to, velocity is equivalent to voltage, B12 is equivalent to 1 by R12, V1 is equal to voltage, velocity V2 is equal to voltage V2, K1 is equal to reciprocal of L1, V1, V1, V2, V2. So this is the equation. Now we are going to, here in current, we have to put all these things in parallel because this is a current source. So I'll start with current source, and here node, we are going to consider node. So in this node, in this junction, this the voltage is V1, and in that junction all the current are joining. For example, this is I1 is coming here, and then capacitor is connected here. This parallel to the current source, that is this one, that is C in a V1 by dt is parallel to current source, and again resistor is parallel to the current source. So all are connected in V1, and common one is R12 and L1 is common. So I am going to, here we are going to put the capacitor and resistance in parallel. At the same time, these two are common to node 1 and node 2. So we are going to put R12 and L1 in parallel, okay, and we are going to consider this is V2, this is the node 2. So first equation is over. Second equation, we take second one and replacing all the terms as per the Ford's current analogy, M2 C2 and dV2 by dt is this is voltage becomes, that is velocity becomes voltage, and B2 one conductance, L2 inductance, reciprocal of inductance. This B12 is reciprocal of resistor, K1 is reciprocal of inductance, and I am simply replacing velocity by voltage. So here R12 and L1 are common to two nodes, that is node 1 and node 2. Node 1 is V1 and node 2 is V2. So I am going to simply put parallel with R12 and L1, and it is connected with the node 2. And in addition to these two things, we have a capacitor and inductors and a conductance. So inductor is parallel with resistor, that is 1 by R2 is conductance, and C2 1 by C2. So this is the circuit. Now we have two different circuit. This is one circuit, and this is one circuit. This is one circuit. Now we are going to combine, and here these two are common. So I am simply joining these two things, and I am finally drawing the circuit. This is the force current electrical analogous circuit of a given mechanical system. This is the way we can draw electrical circuits. Electrical in the sense force, voltage and force current electrical analogous circuit for the given mechanical translation system. Thank you very much.